Well, look at us. We as a species have come a long way since discovering fire, agriculture, industrialization, all up to this point. And yet at every stage of this history, we have wondered upon one question. How can we do what we do? What allows us to think, imagine? What makes us intelligent? And philosophers, thinkers, neuroscientists, psychologists have pondered upon this question for eras across civilizations. But we stand at this unique point of time in history where we have access to artificial intelligence systems. AI systems that are systems built by us. They can do complex things, and they're way more accessible than any brains out there. We don't need to open up skulls, stick sensors in the brain. We can just look at our code and figure out what are the complex processes underlying intelligent behavior. But you must be thinking, wait a second. Brains and AI are not the same thing. One is a living organism and one is a silicon-based chip. Well, this is where I come in. My research has been to kind of create this framework to compare intelligent systems across biological intelligence, synthetic intelligence, and kind of create these pillars across which we can study these systems. For today, let's focus on the representation pillar of this framework. What are representations? Well, representations are basically how a system perceives, processes, and stores information about an input. For instance, let's say I give you, an intelligent organism, this very difficult task of looking at images of dogs and cats and just segregate into different species or different breeds. Very quickly, you'll realize you need to focus on certain features, maybe the color of the fur, the shape of the ear, and very quickly you'll realize two problems. You focus on too few features, and it's a very difficult task. You focus on too many features, it gets very overwhelming. This is what I call as the capacity robustness dilemma. And it turns out the way our brains solve it is they encode many features, but they give different weightage or importance while focusing on these different features. As it turns out, my research shows that advanced AI systems have a very similar property. In fact, you can actually look at this weightage profile and identify what is a good versus a bad AI system. What I've also been developing is a mathematical framework to understand what these features are and then work with experimentalists to test if a brain does the same thing. You must be thinking, okay, great, but why does it matter? Well, it matters because if there exist shared principles of intelligence, we can actually use complex biological mechanisms to improve our AI systems and use AI systems to better understand our brain, both its functionalities and dysfunctionalities. Well, I, for one, hope that this framework will help us explore these synergies between brains and AI systems and help us uncover and understand those principles of intelligence, not just synthetic or biological, but what drives intelligence. Thank you.